I have a little picture here. This is starting on section 1.5, which is on continuity, and since I'm doing another video, I'll bring out, this is math 65 calculus. This is on continuity. So definition of continuity. F is continuous. At a point. X equals C. If. The limit as x approaches C of f of x. Equals f of C. Like you plug in C, you get f of C and it's good. But the limit thing is really what's changing on this up. What this implies three things. A,
Shows F your asymptote switch.
there's more, there's even more than that. It implies f of C is defined. Like we can't have infinity. B, the limit as x approaches C of f of x exists. Which means approach from left and right is the same. And that limit is actually f of C. So one of them's already like part of it already. So things that make it discontinuous. Or discontinuous. Or a discontinuity. At C. When f of C is undefined, that would break it. To the. Something that will break it is if the limit does not exist. Like if it's approaching infinity. Or if like it doesn't actually equal f of C. The limit can exist. But if it doesn't equal f of C, it's not continuous there. What this all really boils down to is no breaks. No holes.
Draw the graph.
If you draw the graph, it's handy. Cause we're gonna talk about where the discontinuities are, and they all have different names. So knowing what type of discontinuity is helpful. Okay. Anyone need a little longer on this? Oh, yeah, a bunch of people are still trying, sorry. Okay, so, we're looking at, look at them one at a time. As x approaches one, what's going on at x equals one? We can see that the limit as x approaches one. Of f of x. Is one. The limit does exist. But. F of one does not. So x equals one is is just called a discontinuity. When x is getting to two. We can see that the limit as x approaches two. Of f of x doesn't exist. Because they're approaching different values, right? From the left and right, they're approaching different values. But. F of two does exist. So since there's actually a point there, we say it's discontinuous there, but we call that gap a jump discontinuity. That explains why it's not continuous there. The graph jumps. Depending on which side you're going, I would call that drop from the left, but from the right, it's got to jump up to get to the next level. So they call it a jump discontinuity. at x equals 3. The limit as x approaches 3 of f of x, looks like it's going to infinity from either side. But again, f of 3 does not exist. And we call this an infinite discontinuity. And then at x equals 5. This is a weird one. The limit as x approaches 5 of f of x is, looks like 3. But f of 5 equals 2. This is just a hole in the graph with a point somewhere else. They call this a removable discontinuity. These removable, this one, like this one is worth seeing where it shows up. Like, I don't know the actual equation that was used to generate it, but like. The limit as x approaches 5 of x squared minus 25 over x minus 5. It's clearly discontinuous here. Discontinuous at x equals 5. But if we factor. Now the problem is gone. It's removed. That's why they call it removable. We can't actually remove it. There is a hole in the graph there. But that's where you get, that's why the line will approach the same value from both sides. And just have a hole there. It's when it has something like this where it is causing a problem. Because it exists in the denominator, but it cancels out. If you actually do stuff like that. That's where you'll see stuff like that. So that talked about continuity at a point. So continuity on an open interval. We say f is continuous. On AB. If f is. Continuous at every point in AB. And for a closed interval. F is continuous on a closed interval. We should call that f of x and keep. Does anyone know what a closed interval is? I don't know how well your algebra teacher taught you. Open, you don't include the endpoints, closed you do. I don't know why they call it closed and open, they just do. They label them differently. If the following conditions are met. A. F of x is continuous on the open interval. So if we're, as long as we're not looking at the endpoints, it's continuous everywhere inside. Then we gotta look at endpoint, like what's happening at the end of these intervals. For B. You know what, I'm gonna use 1, 2, and 3, because I have A and B as my interval and that's confusing. So 2. The limit as x approaches A from the right of f of x equals f of A. Which means it's like continuous. From the right at A. And 3 is gonna be about B. Limit as x approaches B from the left. Of f of x equals f of B. So continuous from the left at B.
When you say from the right to the left, you mean, it goes from infinity to the point A or B, or?
It doesn't need to be from infinity, but just somewhere from near it. As you approach it from that side. So like. Let's say this is A and this is B. And I can have it longer than that, but like. There's f of B. And let's just say we are looking at. That region right there. So like this is continuous everywhere inside. And the limit as x approaches A from the right. This is part 2. Is actually equaling f of A. It's approaching that point. And for like part 3. As we come in from the left at B, that's f of B. And 1 is like the middle. So we don't wanna have like a jump discontinuity at the end. Or removable discontinuity at the end. Pretty much, if you can draw the graph without lifting your pen or pencil, it's continuous. That's a very safe way of looking at it. Anyone need this? I see a couple kids somewhere. Got one more row to add and then we're gonna give you guys some stuff, some examples to try, figure out what they are. Really need to change the order on my notes, this definition needs to come before my example. Everyone ready? Does anyone need longer? Okay. So one more thing to add, so we talked about on an interval, but like, what about the entire function? We define a continuous function. To be one. That is continuous. At every point in its domain. I hate this definition, I really do. You'll see why. So like f of x equals 1 over x. It looks like this. Got an asymptote for the y-axis. Its domain is negative infinity to 0 in union with 0 to infinity. So they say f of x equals 1 over x is continuous on its domain. These are two open intervals and everywhere in that open interval is continuous. But f of x is not continuous. On any interval containing 0. So let's play. What can you say about the continuity of the following functions? Everybody didn't say fire, but okay, good. You guys think about this one. What? It's worth trying to graph. Try graphing it. Like we can see the y-intercept is 16. And if you factored this is 4 minus x, 4 plus x. So if we set that equal to 0. We have at 4 and -4. That x squared is a parabola, but the negative is making it go downward. Are there any holes? It's continuous. F of x is continuous here. And it's continuous everywhere. Which is true for all polynomials. Remember, polynomials are like Cn x to the n plus Cn x to, or n minus 1, x to the n minus 1. And we go down to C1x plus C0. N is just greater than 0, or greater than or equal to 0. You can't have negative exponents. That's what makes a polynomial. That's what a polynomial is. So we don't have any negative exponents, we're good to go. Ready for Mark?
Oh, wait. Yeah, I'm ready.
Everyone else ready? Alright. So I'll give you time, give you guys time to work on this, think about like, talk to a neighbor. If you feel like it. What can we say about continuities or discontinuities? And is it continuous on its domain? Definitely encourage you to talk to the people around you. No man is an island. No matter how badass you are.
I got this is a straight line.
What?
Isn't that just kind of a straight line or?
It's actually gonna look kind of like a straight line, but. Check with your neighbors. We'll do it together in a second, but. Check with your neighbors. If you guys, and the person next to you get the same thing.
And then what is it? It's continuous as well.
Yes, well. Discontinuous. Do you have to put in yes, if it's continuous or discontinuous?
Let's talk about the continuity, is there any discontinuities, is it
Oh.
continuous on its domain? Uh. Where is it continuous,
Yeah.
kind of thing?
Next. You do it's
Let's just,
equals
it starts in,
plus. Sorry.
it's. Axis 6.
Well, we could start right, is there a discontinuity?
No,
Yeah, there is,
That's it.
at 6. If I plug in 6 right now, I get a 0 on the bottom. So this is definitely discontinuous. Why did you say that?
because I thought if we factored it out, we would have x plus 6 left.
That's what I figured you were gonna do, so let's talk about that.
X plus 6 equals 0.
So we factor that out. And we get f of x equals. X plus 6, right? When that happens and we no longer have an issue, we're gonna call that a removable discontinuity. Since I was able to remove it by some manipulation. The function. So the function's domain can include everything but 6.
So they're almost like trying to trick you into thinking that. It's continuous and you just gotta realize that it's not gonna, that it's only. Discontinuous at 6.
Yeah.
Okay.
And if you try to look at the shit on Desmos. It's gonna look like a straight line. You have to literally put your cursor over the. The value x equals 6, and it'll say 6 comma undefined. But it doesn't matter how much you zoom in, it looks like a straight line. So sometimes tech won't help you. So, but that is its domain, so it is continuous on its domain. And since it's continuous on its domain. We call it a continuous function. I like the definition, but. I didn't make the rules.
Even so, in this case, even though there's a discontinuity, I mean, physically there's discontinuity, because it's continuous in the domain. It's still a continuous function.
Yeah. Which to me sounds like bullshit, cause there's a hole in the fucking graph. That's just how they define it. I don't know why. Maybe because you don't work with functions outside their domain. That might be why they're going with it, like, we just know 6 doesn't work here. That might be what they're doing with it. Seems like a arbitrary decision. It sounds wrong to me, if it sounds wrong to you, you're not alone. Like, there's a hole in the fucking graph, why are we calling it continuous? Alright, so what about? F of x equals. -1 over x squared if x does not equal 0. And it equals 3 if x equals 0. Oop. Or maybe sketch it.
Three on the line.
So like, what happens when X gets really, really large?
It runs along x equals 0, as in.
Yeah, it looks like it's going to zero there. What about as it gets close to zero?
On the y, or
Like 1 over like 0.00000001.
starts going,
It's gonna start going down that.
yeah,
A number over a decimal is infinity, like as its number goes to zero on the bottom, it's going to infinity, but the negative is making it negative. If we stick in negative infinity, it's doing the same thing, it's going over that way. And if we approach zero from the left, it's still doing that. But at x equals 0, we have this. So, is it continuous? Or where is there a discontinuity? There's a discontinuity at x equals 0, right? If you're unsure about it and don't do the graph, another way of doing it is go, okay. Clearly, if there is a problem, it's gonna be around 0, so like, let's check the limit. Limit as f of x, oops. That's not how we write limits, limit as x approaches 0 of f of x. It looks like it's going to negative infinity. But that does not equal f of 0. Which is 3. Negative infinity does not equal 3. That was one of the rules for continuity, they had to equal. So that's one way of showing it without a graph. This is an infinite discontinuity. It's kind of a jump discontinuity too, because there's actually a value there. I don't know, maybe they call it a infinite jump discontinuity. This seems weird. There's like a lot of shit going on there. Is it a continuous function?
I see it.
And if so, what?
Well, first of all, the graph, I think there's no holes in it, so be continuous, right?
Well, we,
Up to-
so when you're saying there's no holes, like. For every x, there's a y, is that what you're saying?
Yeah.
Okay. So the function's defined everywhere. Right? That's what you're going with.
Yeah, but the issue is at 0.
The issue is at 0, is it continuous there? No, it's not continuous at 0. It is defined at 0 though. So this is not a continuous function. Because 0 is part of its domain.
Domain, please.
Negative infinity to infinity. It's valid everywhere. There is a y value for every x. It's irritating, right? Because like just, and it's because it's this piecewise type of function. It happens when, it can happen, I should say. It can happen when there's piecewise functions. Like if I had done, we're gonna do another one later on, but I'm gonna hit that x squared minus 36 again. That one we just did up there. If I instead had made that one up there. F of x equals x squared minus 36 over x minus 6. If x does not equal 6. Or it equals 12 if x equals 6. This is now a continuous function. Or this was a continuous function already, but this is continuous. Continuous on negative infinity to infinity now. Because even though this part is a continuous, when we actually do x equals 6, remember this reduced to x plus 6? So 6 plus 6 equals 12. The limit did approach, it approaches 12 from both sides, and it's defined to be 12 at 6. So I can have a piecewise function that's continuous on negative infinity to infinity. But it requires. This is like having x plus 6 is like this, it's doing this. That's the A part. And then the B, like A's there and B's here. And this is at 6 and B fills in the 6. So like I have a complete line. There would be no reason to write f of x like this. You would just write x plus 6. But you never know, I mean. It happens, so. It's irritating, I agree, I told you in the beginning, I don't like this definition of continuous functions. But that is how they define it, so you're just gonna have to like. You need to be able to connect the dots everywhere, basically, to make it continuous. On its domain, and domain is simply where, is there a y value for that x there? So even though on this one up here. This part didn't have a y value for x equals 0. This part did. So it is defined at x equals 0. We actually have a point there, we saw it on the graph. Alright, I will see you guys on Wednesday, we'll finish up 1.5, and still a little bit more going on in here. Thursday. Sure, why not? Sure you don't wanna do it tomorrow during my trig class, I can try to trig and calc at the same time.
I don't want that shit again.
That ain't happening. Have a good day, I'll see you guys Thursday.